Your existence required the death of multiple massive stars. Not metaphorically, literally. The carbon in your DNA, the nitrogen in your proteins, and the phosphorus in your cell membranes could only exist because these stellar giants exploded billions of years ago in exactly the right sequence. New 2025 studies confirm each essential element's formation depended on very specific stellar conditions. The phosphorus that powers every cell in your body forms only during the final seconds of certain dying stars. The implications of what researchers have discovered will change how you think about being alive. To understand this cosmic connection, we need to trace the manufacturing process that created you. The journey begins at the most advanced observatories on Earth, where scientists monitor the stellar factories that forge the elements of life. The Stellar Assembly Line of Life. ALMA's network of giant dish antennas captures the faint radio signals from stellar cores, where temperatures reach 100 million degrees and atoms transform into the building blocks of life. These instruments reveal how the universe operates as a vast manufacturing system, creating the elements essential for biological chemistry through processes that span billions of years. Recent ALMA observations show something remarkable about cosmic manufacturing. Star formation across the observable universe has slowed dramatically over the past 5 billion years, with current measurements indicating that most of the cosmic assembly line still lies ahead of us. The universe has barely begun creating the heavy elements necessary for complex chemistry. Inside stellar cores, different-sized stars operate as specialized factories. Stars 8 times more massive than our Sun reach core temperatures of 3 billion degrees, where carbon atoms form through the triple alpha process. 3 helium nuclei collide in rapid succession, creating carbon-12, the backbone of organic chemistry. Stars between 8 and 25 solar masses continue the assembly line, fusing elements in concentric shells around an iron core. The timing of these nuclear reactions follows precise sequences that determine which elements can exist. But phosphorus presents the most challenging manufacturing requirement of all. This essential component of DNA and cellular energy systems demonstrates just how extraordinary stellar chemistry becomes. Phosphorus can only form in stars between 15 and 25 solar masses during explosive silicon burning that lasts mere seconds before core collapse. The narrow mass range and brief production window make phosphorus the scarcest biological element in the universe. When massive stars exhaust their nuclear fuel, gravitational collapse triggers explosions that distribute their manufactured elements across space. Type II supernovae from stars above 25 solar masses release carbon, nitrogen, oxygen, and phosphorus in characteristic ratios. These explosions inject fresh, heavy elements into surrounding gas clouds at velocities exceeding 10,000 kilometers per second, spreading them across hundreds of light years. Type Ia supernovae contribute a different elemental cocktail to cosmic chemistry. These explosions occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass threshold. The resulting detonation produces large quantities of iron, nickel, and cobalt, while creating smaller amounts of the lighter biological elements. This dual supernova system ensures that interstellar space receives both the structural elements for rocky planets and the transition metals needed for complex biochemistry. Spectroscopic analysis reveals dramatic metallicity gradients across spiral galaxies. The central regions contain 3 times more heavy elements than outer spiral arms, creating zones where planetary systems inherit vastly different chemical inventories. Our solar system formed in a galactic sweet spot, where multiple generations of both supernova types had enriched the local environment to optimal levels for biological chemistry. The Milky Way's chemical evolution spans 13 billion years of stellar processing. First-generation stars contained only hydrogen and helium, making planets and life impossible. These primordial giants lived brief lives before exploding and seeding space with the first heavy elements. Second-generation stars incorporated this enriched material, continuing the manufacturing process and producing more diverse chemistry upon their deaths. Our Sun represents a third-generation star born from gas clouds already enriched by billions of years of stellar processing. Isotope analysis of meteorites shows that our solar system's formation incorporated material from at least 50 different supernovae explosions. Each contributed specific elements in characteristic ratios, creating the precise mixture needed for terrestrial planets and biological chemistry. The chemical signatures in stellar spectra tell the story of galactic enrichment over cosmic time. Stars formed 12 billion years ago show metal abundances 1/100th of solar values. 8 billion-year-old stars contain 1/10 the heavy element content of our Sun. This steady increase in metallicity created an expanding galactic zone where planets could form with sufficient heavy elements to support complex chemistry. Stellar winds from massive stars also contribute to element distribution between explosive events. These continuous streams of particles carry newly synthesized elements into surrounding space at gentler velocities than supernova shockwaves. Wolf-Rayet stars lose up to one solar mass every million years through powerful winds enriched with carbon, nitrogen, and oxygen from their exposed stellar cores. The interaction between stellar winds and supernova explosions creates complex mixing patterns in interstellar space. Computer simulations show how multiple stellar generations work together to homogenize element abundances across galactic regions. This mixing process ensures that when new stars form, they incorporate representative samples of all previous stellar nucleosynthesis. ALMA observations track this ongoing process by monitoring molecular clouds where the next generation of stars will form. These dense regions already contain water, carbon monoxide, and dozens of other molecules built from stellar-manufactured atoms. The chemical complexity increases in regions that have experienced recent supernova activity, showing how stellar death directly enables the formation of complex molecules needed for life. Modern stellar archaeology techniques allow astronomers to trace individual stars back to their birth environments and identify which ancient supernovae contributed their atoms. The European Space Agency's Gaia mission has mapped the positions and chemical compositions of over 1 billion stars, revealing how element abundances vary across different stellar populations and galactic regions. The stellar assembly line continues operating throughout the observable universe, but its productivity has peaked. Current star formation rates suggest that galaxy-wide chemical enrichment will plateau within the next few billion years as available gas supplies become depleted. This makes our current epoch special in cosmic history. We exist during the most productive period of biological element synthesis. Each atom in your body carries the fingerprint of stellar nuclear processes that occurred across billions of years of cosmic time. The oxygen you breathe formed in stellar cores 20 times more massive than our Sun. The calcium in your bones crystallized from gas clouds enriched by hundreds of ancient supernovae. But the stellar connection to life extends far beyond the atoms themselves. The same explosive events that created your elements also launched invisible messengers across the galaxy, carrying information and energy that continues to influence biological processes in ways scientists are only beginning to understand. Cosmic radiation, the universe's hidden influence. These invisible messengers reach Earth through the most sophisticated detection systems ever built. Deep within Antarctica's frozen landscape sits the IceCube Neutrino Observatory, where scientists track particles that pass through the entire planet undetected. The facility consists of 5,000 digital optical modules suspended throughout a cubic kilometer of ice, capturing brief flashes of blue light when high-energy neutrinos interact with ice molecules. The 2025 data from IceCube has identified specific supernova remnants as sources of the highest energy cosmic ray particles reaching Earth. These discoveries reveal that stellar explosions continue influencing planetary environments long after their visible light fades. Multi-messenger astronomy now combines neutrino observatories with gravitational wave detectors and traditional telescopes to create complete pictures of how massive stellar deaths accelerate particles across the galaxy. Cosmic rays transport far more than energy across interstellar space. High-energy particles carry complex organic molecules attached to interstellar dust grains across distances spanning hundreds of light years. Amino acid precursors and simple sugars survive these journeys by binding to carbon-rich dust particles that shield them from destructive ultraviolet radiation. These molecules arrive in stellar nurseries where new planetary systems form, seeding them with preformed biological building blocks. Our solar system's journey through the Milky Way exposes Earth to dramatically varying cosmic ray intensities. As we orbit the galactic center every 225 million years, we pass through spiral arms where recent supernovae have enriched the local environment with high-energy particles. Current measurements show cosmic ray flux increases by 30% when our solar system travels through these active star-forming regions compared to quieter spaces between spiral arms. Ice core samples from Greenland and Antarctica preserve records of cosmic ray intensity fluctuations over the past 800,000 years. These data reveal clear correlations between cosmic ray bombardment and major climate transitions throughout Earth's history. Periods of increased cosmic ray exposure correspond to ice age cycles, suggesting that stellar explosions in our galactic neighborhood directly influence planetary climate systems over geological timescales. When cosmic ray particles enter Earth's atmosphere, they create cascades of secondary particles that penetrate to ground level. A single high-energy proton from space generates showers containing millions of muons, electrons, and photons that spread across several square kilometers. These particle showers continuously bombard every living organism on the planet's surface. The average human body experiences several cosmic ray interactions every second, with particles passing through cellular structures and occasionally damaging DNA molecules. Lightning formation depends heavily on cosmic ray ionization of atmospheric gases. High-energy particles create pathways of charged atoms that provide initial channels for electrical discharge between clouds and ground. Regions with higher cosmic ray flux experience increased lightning activity, which drives atmospheric chemistry reactions that produce nitrogen compounds essential for plant growth. Global lightning frequency varies with cosmic ray intensity, creating connections between distant stellar explosions and agricultural productivity on Earth. The 2025 research from the CERN Cloud Experiment demonstrates that cosmic rays create condensation nuclei necessary for cloud formation in Earth's atmosphere. High-energy particles ionize water vapor and atmospheric gases, generating microscopic particles around which water droplets form. Variations in cosmic ray intensity directly affect global cloud cover, which regulates planetary temperature through changes in solar radiation reflection. Cosmic ray flux measurements show 22% variations that follow our solar system's vertical oscillations above and below the galactic plane. When we travel through regions with higher stellar density, increased supernova activity boosts local cosmic ray levels. These oscillations occur over periods of 30 to 40 million years, matching timescales of major mass extinction events in Earth's fossil record. The correlation suggests that our planet's biological history reflects the rhythm of our journey through galactic space. Atmospheric chemistry models reveal that cosmic rays drive the formation of hydroxyl radicals that control the breakdown of greenhouse gases like methane. Higher cosmic ray intensity accelerates methane destruction in the upper atmosphere, reducing its warming effect on global climate. This process creates feedback loops where stellar activity in distant parts of the galaxy influences Earth's atmospheric composition and surface temperature. Biological research demonstrates that cosmic ray exposure influences cellular repair mechanisms across all life forms. Organisms in high-altitude environments show enhanced DNA repair capabilities compared to sea-level populations, suggesting evolutionary responses to increased cosmic radiation. The repair systems appear optimized for the specific types of genetic damage caused by cosmic ray interactions, indicating that stellar radiation has shaped biological evolution at the molecular level. Modern satellite networks monitor cosmic ray intensity in real time, revealing how solar activity modulates the interstellar radiation reaching Earth's atmosphere. During periods of high solar wind activity, our star's magnetic field deflects low-energy cosmic rays, reducing their flux by up to 50%. This solar shielding effect varies with the 11-year solar cycle, creating regular fluctuations in cosmic ray exposure that correlate with changes in atmospheric chemistry and climate patterns. The discovery that cosmic rays carry organic molecules across interstellar distances fundamentally changes our understanding of how biological chemistry develops throughout the galaxy. Complex carbon compounds survive journeys lasting millions of years, while attached to dust grains accelerated by supernova shockwaves. These molecules arrive at stellar nurseries chemically intact, providing shortcuts for the development of biological systems on newly formed planets. Space-based detectors reveal that the highest energy cosmic rays originate from stellar explosions occurring within our galactic cluster, rather than from distant galaxies. Every breath we take occurs while high-energy messengers from ancient stellar explosions pass through our bodies, connecting us directly to the explosive deaths of massive stars. But these cosmic messengers represent only part of the stellar influence on biological chemistry. The space between stars harbors its own chemical secrets, where temperatures near absolute zero hide surprising molecular complexity. The molecular factories between stars. At the Space Telescope Science Institute in Baltimore, astronomers sit before massive screens displaying infrared images that reveal the chemical secrets hidden in the emptiness between stars. The James Webb Space Telescope operates 24 hours a day, collecting light from molecules floating in regions so cold and empty that they seemed lifeless until recently. These infrared signatures tell a different story about interstellar space than anyone expected. The Observatory's instruments detect molecular fingerprints across wavelengths invisible to human eyes. Each molecule absorbs and emits infrared light at characteristic frequencies, creating spectral lines that identify specific compounds scattered throughout the galaxy. Water molecules appear as distinctive peaks at 6.2 micrometers. Methanol shows up at 9.7 micrometers. Carbon dioxide creates sharp absorption features at 15.2 micrometers. The telescope catalogs these signatures automatically, building databases of cosmic chemistry that grow larger each day. Scientists working with 2025 JWST data have confirmed the presence of over 300 different organic compounds drifting through interstellar space. These molecules include formamide, acetaldehyde, and glycolaldehyde direct precursors to amino acids and sugars. The abundance surprised researchers who previously assumed that complex chemistry required planetary surfaces or stellar atmospheres. Instead, the vacuum between stars hosts an active molecular laboratory operating on scales spanning hundreds of light years. Molecular clouds represent the most chemically active regions in interstellar space, despite temperatures that drop to within 10 degrees of absolute zero. These dense accumulations of gas and dust contain enough material to form thousands of stars, yet they remain stable for millions of years before gravitational collapse begins. Inside these frigid environments, Molecules that would decompose instantly at room temperature persist for geological timescales, while participating in slow chemical reactions. The Orion Nebula contains molecular clouds where temperatures reach 4 Kelvin cold enough to freeze nitrogen solid, yet spectroscopic analysis reveals dozens of organic compounds forming continuously. Hydrogen sulfide reacts with carbon monoxide to produce complex sulfur-bearing molecules. Ammonia combines with formaldehyde to create methylamine, a compound found in living cells. These reactions proceed through quantum tunneling effects that allow atoms to cross energy barriers impossible at higher temperatures. Cosmic rays penetrate these dense clouds and provide the energy needed to break chemical bonds and create reactive molecular fragments. When high-energy protons strike ammonia molecules, they knock off hydrogen atoms that immediately react with nearby carbon monoxide. The process creates formamide, which serves as a precursor to nucleotide bases found in RNA. Similar cosmic ray interactions convert simple alcohols into aldehydes that participate in sugar formation, pathways identical to biological processes. Interstellar dust grains function as microscopic reaction vessels where prebiotic chemistry occurs. These particles measure less than 1 micrometer across, but provide surfaces where gas-phase molecules can stick and interact. Silicon-rich grains attract water molecules that freeze into thin ice mantles. Carbon-rich grains collect organic vapors that condense into complex molecular films. Each grain operates as an individual chemical laboratory with its own unique reaction environment. The ice mantles surrounding dust grains create surprisingly complex reaction networks. Water molecules form the foundation layer, followed by methanol, formaldehyde, and carbon monoxide that freeze in successive layers as temperatures drop. Cosmic ray bombardment provides energy to break bonds within these ices, creating mobile radicals that migrate across grain surfaces and combine into larger molecules. Laboratory experiments reproducing these conditions generate amino acids, fatty acids, and even nucleotide components from simple starting materials. Grain surface reactions follow pathways that mirror biochemical processes found in living cells. Hydrogen atoms landing on icy surfaces react with carbon dioxide to form formic acid, then methanol, then more complex alcohols. These alcohols interact with ammonia-rich regions to produce amines and amides. The sequential addition of carbon atoms builds molecular chains identical to those found in meteorites and cometary samples. The similarity suggests that life's chemical foundations form naturally, wherever the right conditions exist. Stellar winds from massive stars carry these molecular building blocks across interstellar distances measured in thousands of light years. Young hot stars emit powerful particle streams that sweep up surrounding dust and gas, accelerating them to velocities exceeding 1,000 kilometers per second. The winds create expanding bubbles of enriched material that merge with other stellar outflows, mixing and distributing organic molecules throughout galactic regions where new star formation occurs. Supernova explosions inject additional energy into molecular cloud chemistry, while dispersing heavy elements needed for complex molecule formation. The shockwaves heat dust grains enough to sublimate their ice mantles, releasing stored organic compounds into the gas phase where they can react with freshly synthesized metals. Iron and magnesium atoms expelled by supernovae catalyze reactions that would otherwise proceed too slowly to matter. The combination creates chemical environments more diverse than any terrestrial laboratory.